Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode Problem 124, Binary Tree Maximum Path Sum. Even though this question is marked as hard, it's actually not that bad. I would personally rate this question more of a medium. The solution isn't really that complicated. I think that it's very intuitive and makes a lot of sense. I'm not sure why it's rated hard. Either way, let's read the question prompt and work through an example. So, a path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that the path does not need to pass through the root. The path sum of a path is the sum of the nodes' values in the path. Given the root of a binary tree, return the maximum path sum of any non-empty path. So if we see this tree here with nodes minus 10, 9, 20, 15, and 7, then the maximum path sum is actually going to be this tree here, where we go from the 15 to the 20 to the 7. Remember that we don't have to pass through the root of the tree, so it's not an obligation to do that. So we can see that, 20 plus 15 plus 7 is going to equal to 42. Right, and let's verify that that works. If we went 7, 20 minus 10, so that would be 27, so minus 10, so 17 plus 9, that's going to be 27. So we know that that path, going here to here would be 27, which is not the maximum. What if we went, 15 to 20, so that would be 35 minus 10, so 25 plus 9. So that would be, 25 plus 9, so that's going to be 34. So obviously that's not greater than that. We could just have the path, for example, just 7 and 20. That would be 27. We could have this, which is 35. We could have, just this path, which is 10. We could have this path, which is 1. We could have this path. So as we can see that, those are all the possible paths. And the best one is actually going to be 15 to 20 and then 20 to 7. So basically this little subtree here. So how do we actually want to solve this? Because we can see that, we have negative numbers, so we can't just assume that, it's just going to be the sum of the entire tree, right? If it was all positive, then, the maximum path, we would just easily be able to optimize that. But because negatives are in play, then sometimes we have to cut a path by not taking it, because, if it flips negative, then, it could potentially not be the global maximum. And one other thing that we have to notice here is that, say we're at this 15 and 7 and we choose, we're at this 20, we have the choice of either connecting the paths, so 20 to 15, then connected with 7, but that means that we're not able to go, any higher in the tree, right? We can't go minus 10 to 20, this would have to be the root of that tree. So at any point, at any node, we have to make a choice between its left and its right subtree if we want to go higher up in the tree, or we can choose this, node here to be kind of the root of the tree, and then we were allowed to take both the left and the right subtrees. So we do have to take that into account when we're doing our, processing. So now let's go into the code editor and write out the code, and we're going to see all the possible cases for this particular problem and how we're actually going to derive our most optimal solution, because there are a few edge cases here that we do need to basically think about. And I guess this is probably why the question is marked hard, because there are some edge cases that may not be obvious at first. So I'll see you in the editor and we're going to write the code. Okay, we're in the editor. Let's write the code. The first thing that we want to notice is actually that our root can be given to us as an empty node, which would be the case that, we're not given a tree, which means that we simply have to return 0, because obviously the maximum path sum of nothing is nothing. So we return 0 in this case, because our answer is going to, looking for an integer. So we're going to say if not root, we want to return 0. Now we want to basically account for the fact that our tree may only have a root. It may not actually have any left and right children. It's just going to be a single, stump node. So what we want to do is we want to set that equal to our initial maximum path sum. In the case that we don't have, any other nodes in the tree other than the root, the maximum path sum should just be whatever the root's value is. and that's what we want to return. And we're going to keep track of, the maximum path sum in a global variable, and we're going to have, a recursive DFS function that's actually going to perform the checks along all the possible, routes in the tree. So we're going to say self.max path sum is going to be equal to whatever the root's value is. And now what we want to do is we want to call our DFS function on the root to basically compute what the maximum path sum is inside of the tree. And at the end, what we want to do is return, the maximum path sum that we've seen. So what we need to do now is actually define the DFS function that's going to do the majority of the work. So let's do that. So we're going to say def DFS, and we're going to take self and a node. So obviously, if we have an empty node here, there's nothing we can do. We have to just return 0. We can't sum anything over a null node, right? Because it doesn't have a .val property, so we can't actually access it. So if it's null, we're just going to return 0. So we're going to say if not node, then we can simply return 0. Because remember, we're going to be summing over the tree, so we don't want to return null here, because if we try to add null to an integer, it's going to blow up and it's not going to work. So that's the case when our node is 0. Now what we want to do is let's handle the case where we're at a leaf. What happens when we're at a leaf, right? We know that leaves don't have children, which means that, we don't have to add anything to its children, check that it's what the route from the children was. We can just return whatever the node value is. So we're going to say if not node.left and not node.right. So basically this means that, the node that we're at is a leaf. We can simply say, let's return whatever the value of our node is. And what we need to do is also check that our current node value is not actually greater than the maximum path sum that we've seen so far. It could be the case that our leaf node, has like a value of 1 billion, whereas the rest of the tree is actually negative numbers. So any path sum that we may have seen so far, would be negative, and this node is actually the greatest in the tree. So we do have to make a check whether or not this node's individual value is greater than the entirety of the maximum path sum that we've seen. So we're going to say self.max path sum is going to be the maximum, whatever the current maximum path sum is, and the current node.val. And then we're simply going to return node.val here. Now that we verified that, okay, we've checked for a null node and we've checked for a leaf node, otherwise it must be a node that's not a leaf and that isn't null. So we're going to go into its left and right subtrees. So we're going to say, the path sum from the left is going to be self.dfs node.left, and we're going to say the path sum from the right is going to be self.dfs node.right. So as you can see, we are performing this in basically a post order manner. So we're going to go into the left subtrees before we go into the right into the parent, right? We're going to go into the left, right, and then we process the parent. So this is a post order traversal. Now what we want to do, that we've processed the left path sum and the right path sum, we have to make a decision of whether or not we want to continue up into the tree, or we want to use the current node as basically kind of, the root of whatever our tree is, and use that to basically compute a path sum. So there's a few options here that we can choose. So, our maximum path sum at this point is going to be the maximum of, whatever the current max is. We always want to check that. And what are our options? So if you remember here, right, if we're at this node 20 and we visited, this subtree and this subtree, the left would return 15, the right would return 7. Remember that we have the choice of either taking, the path between 15, 20, and 7, or we can take the path from 15 to 20 and then go higher up the tree in the hopes of finding a better path, or we can take 7, 20, and then go higher up the tree, or we can say, actually, we can just take 20. If these were both negative, we don't have to take these paths. We can simply just take the 20 and then go higher up the tree. So those are our options. So the maximum at this point is going to be the maximum path that we've seen so far, the current node's value, the current node plus the left path sum plus the right path sum, Then it's going to be the node.val plus the left path sum. So this is the case that we're ignoring. Oops, this should be our path sum. So this is the case where we take, both paths and we don't go higher up in the tree. And, node.val here is if we're ignoring the left and the right. And here we're taking the left but ignoring the right. And then the only thing left is to take the right and ignore the left. So we're going to say node.val plus our path sum. And that's going to be the maximum path that we can form at this current point, given our left path sum, right path sum, and the value of our node. Now we need to decide how we actually want to proceed up into the tree, right? We have to return something from this function because some other function is called, DFS on us, and it expects a left path sum or a right path sum, depending on where we are in the tree. So we need to return something to the next level. And essentially what we're going to do here is what we want to, very similar to what we did before, and that we need to return whatever the maximum path we can take. But remember, if we go up the tree, that means that, we're not able to take, 15 to 20 to 7. We have to make a choice between 15 or 7. We can take one or the other. We can take none of them, but we can only take one. Or we can just take the node value, or if this value is actually small enough, we can just return 0. We can just not take anything. So those are our 4 options, right? We can return, this should be the maximum of, node.val. We can do node.val, and we can take the left path sum. We can do node.val plus the right path sum. And then we can also just do 0 in the case that, if this node, and this node were all extremely small numbers, so basically negative, really small negative numbers, then it could be the case that we just want to ignore all of them. We don't want to take it because that could screw up our maximum path sum, globally if we were to take that. So we want to take whatever the biggest thing we can in a greedy manner. So that's going to be the code for this problem. Let's submit it, make sure that it works. And it does. Cool. So I think at this point, it's good to walk through an example to see exactly how this is going to work. So let's start and kind of draw out this code here. So we're going to start. And the first thing that we do is we check, okay, we're going to work with this tree here. And we're going to say, all right, well, were we given an empty tree? No, right? We were given a root here. So, we do have some processing to do. So the initial maximum path sum is going to get set to whatever root.val is. So root.val, as we can see, is minus 10. So our max is going to be minus 10. And at this point, we need to call the Dfs function on our root and process it. So we call the Dfs on this node minus 10, and we can see, okay, does this node exist? Yes, it does. So that means that, we have to go to the next level. Is this node a leaf node? No, it has a left and a right tree. So that means that it's not a leaf. So that means we need to call into its left subtree and its right subtree. So obviously the left gets processed first. So what ends up happening is we go into the left subtree and we see, okay, now we're in this Dfs function again, and we're at this 9. So this 9 happens, and okay, does it exist? Yes. Is it a leaf? Yes. Okay, so now we need to update our maximum path sum with the maximum of whatever the current max is and our node value, which is 9. So obviously 9 is greater than negative 10, so our new max becomes 9. So at this point, we try to go into its left subtree, but obviously it doesn't have one, so we just return 0. It's right. Actually, no, we don't even get to this point. Sorry, we return node.val here because it's a leaf node. So the 10 is going to receive a 9 from this side. Cool. Now we need to do the right side of 10. So let's call, our Dfs function on the right side of 10. So we're at this 20. So 20 exists and it's not a leaf. So that means we go into its left subtree and we get to this 15. So 15 exists, so we don't do anything here. And 15 is actually a leaf node. So we again fall into this statement here. So now we need to double check, okay, is our maximum, is 15 greater than the maximum we've seen so far, which it is, because obviously 15 is greater than 9. So we're going to update our max, so it's now 15, and we're simply going to return node.val. So from its left subtree, this 20 is going to return 15 is going to get a 15, right? But we still need to do the right path sum. So we go into the right tree and we see, okay, this 7 node here exists, but it is a leaf node. So let's do our check again. Is, the value 7 greater than our maximum 15? No, it's not. So we don't do any update here, but we do return node.val. So now we're back at this node 20, and from the left we've received a 15, and from the right we've received a 7. So now it's time to check our maximum path sum. So remember that the maximum path sum is going to be, the maximum of what we've seen so far. It could be, the maximum of just the node value, or we could take the left and the right, or we could do the node value plus the left, or we could do the node value plus the right. So obviously here, the maximum path is 15, node.val is 20, node.val plus left path sum plus right path sum is going to be 20 plus 15 plus 7, which is our maximum. So this is going to be, 42. So we update our maximum path sum to now be 42. And what we need to do now is return the maximum of whatever our node.val is, or node.val plus the left, or node.val plus the right, or 0 in the case that, everything was negative. But in this case, they're all positive, so nothing happens there. So what's the maximum here? Well, we can see that the maximum is going to be 20 plus 15, so 35. So we're going to return 35 here. So now we're back at this 10, and remember from the right side, we saw that the, we received 9 from that DFS call. And then from our right side, we just saw that we returned 35. So now we do this check again. So what is going to be the maximum? So we're going to try to, take the maximum of whatever the current max is, our node.val, which is minus 10, or minus 10 plus 9 plus 35, which is going to be 44 minus 10, so 34, or, minus 10 plus 9, which is 1, or minus 10 plus 35, because that's the right side, which is, 25. So we haven't found a better maximum. So our max is still 42, so no update happens here. And then what we do is we return the maximum of node.val, so the maximum of minus 10 or minus 10 plus 9, which is 1, or minus 10 plus 35, which is 25, or 0. So obviously 25 is the largest, so we would return 25 here. But since this is the root, we return, and now our DFS is actually finished. So we don't have to worry about anything more. So now we're here, and all we have to do is simply return the maximum path sum, which we saw was 42. So what is the time and space complexity of our algorithm here? Well, time complexity wise, we have to traverse the entirety of the tree. And we're doing a post-order traversal here, but I guess the traversal method doesn't really matter. We have to test every single node in the tree and, perform these computations. All of these, internal computations are going to be constant time calculations, but the fact that we have to visit every single node in the tree means that our runtime complexity is going to be big O of n. Space complexity wise, we're not actually defining any variables other than our maximum path sum here, although this is going to be a constant space allocation. So the space complexity is going to be big O of 1 if we're not counting recursive stack space. Otherwise, it's going to be big O of n, so if we're counting the recursive stack space. So this is always something you want to kind of bring up to your interviewer, be like, well, do we want to count the recursive stack space? Because, technically it is a memory cost. So, that's going to be our time and space complexity for this algorithm. Like I said, it's not the most complicated problem. It is marked as a hard, although I think that it's not too hard to wrap your head around the solution. I think it's very similar to a lot of, DFS type problems that you're going to see on Leetcode. The pattern is very similar, right? This is just a standard post-order traversal. I think the difficulty of this problem just comes in seeing a few of these edge cases here in terms of like setting the maximum path sum and also what to return to the next level. Because remember that you will have, negative numbers which can skew your computation. So sometimes you may not actually want to take a node value And I think we already submitted it, but just to double check, yeah, okay, we did. So yeah, our solution works. Like I said, it's going to be big O of n on the time and constant space in the space, or big O of n on the space if we want to count the stack frames. Anyway, if you've enjoyed this video, please leave a like, comment, and subscribe. Let me know if there's any other videos you'd like me to make, any topics you want me to cover. I'd be happy to do that for you guys. Just let me know in the comment section below, and I'll get back to you. Otherwise, happy LeetCoding.